In the last video, we learned how to integrate sine to the odd power or cosine to the odd power. Now we're going to notice that it actually can be times the other one to any power. For example, as long as we have exactly one, or at least one, I should say, odd exponent, then we can use that same strategy. So we've got an odd exponent for the sine of x. So if we save one of those factors of, yikes, of sine of x for the u substitution, and then the leftover even number of factors will be converted using the Pythagorean identity, then it doesn't matter how many cosines of x we have floating around. They'll just get added on to the cosines of x that are here. What I mean by that is we'll still go ahead and convert this to a 1 minus cosine squared of x. And we're not going to change this other one. We're going to leave that as a cosine to the fourth of x because everything is cosines except for this one sine. So we can go ahead and let u equal not the one we saved. We want the one that gets used over and over again. So that when you differentiate, you get the one that was saved. So that means that we have over here, we've got a negative integral of 1 minus cosine squared is u squared times cosine to the fourth is u to the fourth. Right? The sine of x dx turns into a negative du. Alright, this is something that we can integrate as long as we remember to distribute properly. So we've got negative the integral of u to the fourth minus u to the sixth du. And u to the fourth goes to 1/5 u to the fifth. U to the sixth goes to 1/7 u to the seventh. And that's it, right? I'll go ahead and distribute the negative. There's no reason to have that factored out, I guess. And maybe I'll put the positive one first. So 1/7 cosine to the seventh of x minus 1/5 cosine to the fifth of x plus c. And there you have it. So that same strategy is going to apply over and over again, as long as you have at least one odd exponent. Here we have the odd exponent on the cosine, so the sine squared stays alone, stays untouched. We will take one cosine of x and keep it aside, and then we've got four more. We want to use that Pythagorean identity, so we'll put a cosine squared in there, and then squared squared will give us the fourth. All right, so that's the same strategy we saw before. So we've got sine squared of x times 1 minus sine squared of x squared times the cosine of x dx. And this time we're going to let u equal the sine of x, which means the du equals cosine of x dx. So when we rewrite this, we've got sine squared is u squared. 1 minus sine squared is 1 minus u squared. We're still going to square that. And then the cosine of x dx changes to a du. And we can distribute everything through. So we've got u squared times u squared times 1, u squared times 2, negative 2 u squared. So negative 2 u to the fourth. And then u squared times positive u to the fourth is going to be u to the sixth. So 1/3 u cubed. This writing tablet is far inferior to my other one. You get what you pay for with the writing tablets. Spend the extra $40 and get the $80 one. Because these $40 ones are not so nice. Gotta slow down. Alright, so our final answer is 1/3 sine cubed of x minus 2/5 sine to the fifth of x plus 1/7 times sine to the 7th of x plus c. All right. So we can see that higher exponents definitely makes the process a lot longer, a little bit more tedious, but not conceptually any harder. So surely if we have only one odd exponent, then nothing problematic is going to happen if we have two odd exponents. We just have to pick which one we're going to save. We're going to save one of the sines and then convert the others to cosines, or are we going to save one of the cosines and convert the other to sines? Well, I'll let you try to save one of the sines. Personally, I don't feel like raising a binomial to the 6th power, so I'm going to pick the smaller exponent. So the sine to the 13th is going to stay sine to the 13th. And then we've got one factor of cosine of x that we're saving for later. The other 6 are going to be put into the Pythagorean identity, right? So 2 times 3 gives us 6. We have to have that squared inside the parentheses so we can use the Pythagorean identity. So everything else is going to work pretty much the same way. Slightly bigger number now, right? Because we have 1 minus sine squared of x, this time raised to the 3rd power. And yeah, now we're going to say, well, we're going to let u equal the sine of x. That way du equals cosine of x dx. So that means that we get sine to the 13th is u to the 13th minus times 1 minus u squared cubed, and then the cosine x dx turns into a du. So we've got I won't try to expand this and distribute the u to the 13th at the same time. I'm likely to make a mistake. So Pascal's triangle, anyone? We've got a 1, 3, 3, 1 going on here. So yeah, that's just applying Pascal's triangle to expand the cube of the binomial. So u to the 13th minus 3u to the 15th plus 3u to the 17th minus u to the 19th. I hate to say it, guys, but this is getting a little bit boring, so I'm going to say etc. I think you got it from there. Because I would like to look at the last possibility, which is the most interesting type. By interesting, I mean challenging. That's when we don't have any odd exponents. We have to use the power reducing identity this time, because if we try to use the Pythagorean identity, then we're going to we don't have that one left over that we can use for u substitution. So you can play around with this. Maybe you can try applying the Pythagorean identity here, but then you're going to have a cosine to the 6th, and I think that's going to be even worse. So I think the easiest way to do this is just go ahead and bite the bullet and use the power reducing identity both times. So if you recall, if OneNote will let me recall, the power reducing identities that we've figured out up here, sine squared had the minus in it, and cosine squared had the plus in it, right? So sine squared has the minus in it, and cosine squared had the plus in it, but the cosine wasn't being squared, the cosine was being raised to the 4th, so we're going to have to square cosine squared to get cosine to the 4th. Yeah, it is that nasty, because what's going to happen, we've got 2 times 2 times 2, or 8 in the denominator. That part's not nasty. But we do have a 1 minus cosine of 2x times a 1 plus cosine of 2x squared. In other words, 1 plus 2 cosine 2x plus cosine squared of 2x. And yeah, we're going to have to distribute the binomial into the trinomial. So I'm going to pause this video because you guys don't need to see me work that out. So in orange, I worked that out, 1 times all of this, and then negative cosine of 2x times all of this, and I combined like terms over here. So we've got 1, we've got a cosine. Those are easy to integrate. And then we've got these other two problems, and we know how to do these now. So I'm going to keep on doing the trig identities, at least for now. We're going to use the power reducing identity again. We're going to subtract the fraction. It's got a denominator of 2. We're going to have 1 plus the cosine of the argument gets doubled, so it's 4x now. This is going to require a u substitution, so I'm going to go ahead and separate that out into a different integral. So then we can combine a bit inside this one and get 1 minus 1/2 is 1/2. And then we've got cosine of 2x. Gosh. And then minus 1/2 cosine of 4x. And that has nothing but terms that we know how to deal with. This one, we're going to have to use that Pythagorean substitution, right? We're going to do, well, cosine squared is going to be 1 minus sine squared. And then we still have another cosine here. So we'll deal with that in a bit. But let's go ahead and finish off this. We've got 1/8. Throw this this writing tablet in the trash. 1/2 x. Cosine integrates to sine. The argument doesn't change, but don't forget the chain rule. We're dividing because we're integrating. The same over here. This negative 1/2 gets divided by 4 to get negative 1/8. So all of that part's done. And we'll go ahead and do the u sub now. So we're going to let u not equal to the one we saved, but the one that we have a bunch of. In this case, we have only 2 factors of it, but sine of 2x. So du equals 2 cosine of 2x dx. So that means we've got the integral of 1 minus u squared. Cosine 2x dx equals 1/2 du, so I'll pull the 1/2 out front. So I'll just finish this so I don't have to rewrite everything. This is going to be 1/2 times u minus 1/3 u cubed. And I can do that last bit of substitution when I write the final terrible answer. I don't feel the need to, we should probably close that parentheses. I don't feel the need to keep the 1/8 factored out of all of this if it's not also going to be factored out of that. So I'll go ahead and distribute this 1/8. So we get 1 over 16 x plus 1 over 16 sine of 2x minus 1 over 64 sine of 4x. It's a 4. Minus 1/2 times u being sine of 2x. And then also minus 1/2 times negative 1/3, so plus 1/6 u cubed, or sine cubed, of 2x plus c. Now, you might notice that we've got a sine of 2x term here and a sine of 2x term here, but honestly, at this point, I am so done with this problem, and I bet you guys are too. So I'm just going to call it a day. And if that's correct, I'm pretty impressed with myself, because there are too many places in this problem for you to make a mistake. But that's the basic idea.